I had taken a very long break for some unknown reasons. Now I have resumed making videos and posting it on my channel. I'm continuing with making videos on two-port networks, and I'll take up a problem for today's video. That is computation of transmission parameters for a particular network. By the way, this is my photograph. Right now I don't have any affiliation, so that's it. Anyway, let's write the problem. All right, so I will write the problem. It goes this way: compute transmission parameters for the given network. For the given network. Okay, here there is one S that is N that is missing. Let me write it. I will type instead. Okay, so let's write the network. This also I'll delete. There is one underscore. All right. Okay, compute transmission parameters for the given network. So the network goes this way. I will write the network now. I have a resistor, one ohm. There are two capacitors, one on either side of 1 ohm. All right, this is how it is. It's 1 farad here, 1 farad here, and our two ports will have 1 and 1 dash as the input terminal, 2 and 2 dash as the output terminal. This is how we understand a two-port network. All right, so we're supposed to find out transmission parameters. So what are transmission parameters? Transmission parameters, in other words, are ABCD parameters. We're aware of that. Right? So in order to obtain the transmission parameters for this network, let us try to write the Laplace transformed network. Let us try to take it in S domain. Okay, Laplace transformed network. Let us try to write the transformed network. The transformed network is network can be written as under. Okay, so we'll try to write the Laplace transform network. I will try to copy the same network. Okay, I will copy the network. I'll paste it over here. I will shrink it a bit, fit it there. I'll now write the transformed network. So what is the transformed values of the capacitor? So when the capacitor is taken onto the Laplace transformed domain, it will have the capacitor. If the capacitor is of C farads, I'll write it down here. If a capacitor has C farads, then it will have an impedance of, rather in the S domain, it will have an impedance of 1 by Cs. Okay, this is the transformed version, okay, of the capacitor. So this you must be knowing. If you do not know, you need to refer to the books and find out. It is simply because of the voltage and current relationship a capacitor has, and from that we can get the impedance. It is that simple. So it is something like voltage across the capacitor 1 by C integral IC dt. Okay, this if you can take the Laplace transform of it with, of course, your zero initial conditions, if you make use of, so that your initial conditions is not introduced, so it will be simply this into I of s. So your impedance will become Vc of s to Ic of s, which is equal to 1 by Cs. Okay, it is that simple. This is how you represent the impedance of the capacitor. In the V to I ratio is nothing but the impedance of the reactance, right? So it is Xc of s. So this is 1 by Cs. So what I mean to say is this becomes 1 by 1 into S, that is S itself, where 1 is the value of the capacitor, C. So 1 by 1 is the capacitor value, C being 1, it is 1 into S, or simply S. Okay, so we're able to write the equivalent impedance, right? So this is 1 ohm. Okay, now all these things are in ohms. Okay, this trivia can be removed. This can be erased. Okay, having written the transform network, we will now try to proceed with ABCD parameters. What are the equations that we have for ABCD parameters? We'll try to recollect so that we don't make any mistake. So V1 equal to AV2 minus BI2, and I1, it's I1 V1 connected to V2 I2, right? So I1 equal to CV2 minus DI2. Okay, so how do we express? It's V1 comma I1, which are dependent variables. They are expressed as a function of V2 and I2. Okay, in other words, the input port parameters are expressed as a function of output port parameters. So we know these relationships, we know these equations. Now if we can make I2 0, what does that supposed to mean? If we can open the port 2 and 2 dash, where do we have I2? We will mark that also, so that we won't make any mistake. Okay, so the output parameters are, this is V2, this is I2, and we have this to be V2, where 2 is, the terminal 2 is at the positive end, 2 dash is at the negative end. How do we say so? Arrowhead indicates a positive polarity, always. So we know this convention. This is V1 with 1 at the positive polarity and 1 dash being negative, and I1 is the current into the port. Okay, positive currents are supposed to be flowing towards the port, into the port. All right, so I1 and I2 are respectively the input current and output current flowing into the port. They are positive currents. All right, so having written this much, if you want to determine ABCD parameters, the problem says determine transmission parameters. Transmission parameters are nothing but ABCD parameters. If you want to determine ABCD, obviously from these two equations, if we can call them as 1 and 2, if this is 1 and this is 2, okay, if we can make I2 0, then we will be able to determine A and C from equation 1 and 2 as a ratio of V1 to V2 and I1 to V2 respectively. So making I2 0 will give us A and C, the values of A and C. Similarly, if we make V2 0, that is you short circuit the port 2, that is V2 0, you will be able to determine B and D parameters. It is as simple as that. Okay, so for this given network, what are the values of A, B, C, D? That is the question. All right. So how do? We look at the port. We try to open circuit the port once and then short circuit the port once and see how equations would appear. Like, we simply apply KCL and KVL. Nothing more than that. Right. So we will try to write step 1. I'll choose a color. My step 1 would be, I'll see if I can, no, it won't. It by default it is taking, this is, I'll draw a box. No, it doesn't work. It doesn't matter. I will write myself. That's better. Okay. So what I mean is, we will write it as a step number 1. In step 1, what I intend doing is, I will open circuit port 2, our output port. Okay, so what by port 2 we mean output port. Output port is between 2 and 2 dash. Okay, so when we open circuit the port, what will happen? In open circuit, you have the presence of voltage. Voltage is definitely available, but there won't be any current because nothing is connected between 2 and 2 dash. You have opened the two ends. So then I2 is 0. This is important. What we mean to say by open circuiting the port is, we don't let the current flow through the port. So I2 is 0. There is no current there. Alright, now we will try to apply V1 to the input port and there is a current flow of I1. Let us see how the equations work out. Okay, so I'll again take back the same network because I need not write it every now and then. I'll copy this network. I'll paste this network. I'll take it here. Now, how was the situation? So we have all these things. Now, the given thing is my I2 is 0. So when will I2 flow actually? If you look at that, I2 will flow when you close this part. I will take this color. If I can connect a load here, for example, then there is a supply here. There is a supply of V1 here. Current I1 is flowing into the network. And there would be a current through the load in this direction. However, there is going to be I2. Alright, so I2 would flow only when there is something connected between 2 and 2 dash as a load. Now, when we talk about open circuiting, what we mean is nothing is connected between 2 and 2 dash. In other words, it's like the given network. The given network is actually output port being kept open. Alright, I suppose this much is clear. Now, if this is the configuration, how do we write the various quantities and how do we write the relationships? Okay, we will try to see what will happen to my equation 1 and 2 with I2 being 0. Okay, so I will even take these equations again here so that I'll copy this. Alright, so I'll paste it here. The equations I'll paste. I will see what will happen with I2 0. Okay, now what is our condition? Our condition is I2 made 0. I2 is 0. So what will happen to equation 1? So my equation 1 would be V1 equal to AV2. Because I2 is 0, BI2 would vanish, which will result in A being equal to V1 by V2. And this is obtained with this condition. This is from equation 1. Okay. So what will happen to equation 2? If I look at equation 2, I will get an equation like this. I1 equal to CV2. Because DI2 would be 0. I2 is 0. So this results in the value of C. Value of C now is I1 to V2. With I2 0. Alright. So in order to obtain A and C, we have to take the ratio of V1 to V2 to get A, I1 to V2 to get C. And these two ratios should be in terms of this 1 ohm, 1 by S and 1 by S. That's our, then the job is done. Alright. So now, what is I2? I mean, if you have to get A, so we need to have V1 and V2. So we have to do that, right? So what we will do is, we will try to get the currents and the voltages alternatively. What I mean to say is, the current I1 is here, the current I2, here it's 0, but there has to be a current in this branch and the current will split here at this junction. One current would flow through 1 ohm and 1 by S and come back, and the other branch current would flow via 1 by S. Or in other words, things are very clear. 1 ohm and 1 by S, these two branches, they carry the same current. And this combination, this series combination, because they carry the same current, they are in series. This series combination is in parallel with 1 by S. This much is very clear, right? But what is the current that is flowing here? We do not know. So we will name that current. Okay, so we will write this current to be, let us I3. I'll use a different color, maybe. Not this again. The one which is not. I'll use this color. I'll call this current I3. Okay, so current I3 flows here also. Alright, this is clear. Now we will try to write an equation for I3. From this network, we will see what is I3. What is I3? It is simple. Voltage divided by impedance. So voltage is V2. The impedance is 1 by S. So this is S times V2. Alright, this is the current. You can call this equation 3 because we tend to make use of this equation. This is equation 3. So we are able to get the current I3. Now we will try to get an equation for the voltage V1. What is the voltage V1? Voltage V1 is the voltage that is appearing across 1 by S. This branch will have a voltage of 1 by S. I mean voltage of V1. Okay, 1 by S capacitive reactance has got a voltage of V1 across it. Okay, so we will write an equation for V1. What I mean to say is we will alternatively write an equation for current and voltage that way if the network is little elaborate or little long. Alright, now we will try to write an equation for V1. So what is V1 equal to? The V1 that is available here is equal to the voltage across this 1 by S branch, which is V2, plus the voltage developed across this 1 ohm branch. What is the voltage developed across this 1 ohm branch? It is the current times the resistance. I3 into 1 ohm. What we are doing is simple Ohm's law and KCL, KVL, nothing else, nothing more, right? So V2 plus 1 into I3. 1 into I3. Alright? Alright, so this is the equation. Now, what is I3? Why am I replacing I3? Because in this, if to get A, we want V1 and V2. So in this equation, we have V1 and we have V2. But this I3 is posing a problem. I3 has to be eliminated. What do we do for I3? We'll substitute for SV2. And that will give the result, right? This is V2 plus S times V2. Okay, so this can be further simplified as V2 into S plus 1. Alright, now we will take the ratio of V1 to V2. Okay, so from this what we can write is V1 to V2. How did we get this? This is obtained with the condition I2 being 0. And this here is nothing but A. Alright, that's A. So this is nothing but my A. And this is equal to S plus 1. Okay. I suppose it's clear. So my V1 equal to S plus 1 times V2. V1 is V2 into S plus 1. Therefore, I am taking V1, I'll shift it to the denominator. This is S plus 1. And eventually this is A. Right? That's all I have done. I suppose it's clear. So I are able to determine the parameter A in terms of the network elements. Okay, so A is S plus 1 or 1 plus S, whichever way we want to write, we can write. So we will write this A is equal to S plus 1. This is my A. Alright. Now, what else can be determined? If you can look at these two equations, with I2 being 0, we can even determine C. What is C? C will give me a ratio of I1 to V2. So we need an equation for I1. So what is I1 from the network? From this network, what is I1? If you look at the network, I1 is the sum of the current I3 plus the current that would flow through this branch of reactance 1 by S. Alright. So what is the current here in this branch? It is the voltage divided by the impedance. So V1 divided by 1 by S is the current here. Plus I3 will give me I1. I will write what I said. Okay. So I1 is simply equal to, one current is I3. The other current that would flow through the capacitor is nothing but the voltage across the capacitor divided by 1 by S, impedance of the capacitor. It is that simple. This is further equal to I3 plus I will take this S to the numerator, S and V1. Okay. So in order to determine C, we have to remember these equations. In order to determine C, I need I1, I need V2. Okay, do I have them? I have I1, fine. But do I have V2? No, I don't have V2. Instead, I have I3 and V1. So I have to eliminate I3 and I have to eliminate V1, replace it by V2. So what do? So we make use of equation 3, which will give me I3 equal to SV2. So now this is equal to, for I3, I will put SV2, acceptable, plus S into. Now what do I do for V1? I'll make use of this A relationship of A. I'll make use of this relationship of A. So V1 by V2 equal to S plus 1, or V1 is V2 times S plus 1. This is V2 times S plus 1. Alright, I suppose it's clear. There's no ambiguity. It's here. You can go back to this equation, V1 equal to V2 times S plus 1. So you can even name this equation 4. So this is obtained from 3 and 4. Okay, we're able to get this result. Now we will try to, take the things together. I1 equal to, so we have SV2 plus S square V2 plus another SV2. Okay, so this is nothing but S square V2 plus 2 into SV2. Okay, I will now take V2 common factor. V2 and I will take even S common, S plus 1. Okay, so what is it I have? I1 equal to, now I am able to arrive at I1 equal to V2 S into S plus 1. Alright, what is C? We will go back and look at what is C. What is C? I1 to V2. And we have this condition I2 equal to 0. That is what we did all along. Right? So I2 equal to 0. What is I1 by V2? We will see. We have I1, we have V2. So we will obtain. Therefore, this will result in I1 by V2. And this is obtained at I2 being 0. This is equal to S into S plus 1. And this is our C. Okay. Therefore, C equal to. Now we will write what is C equal to. Therefore, C equal to S into S plus 1. I'll put it, enclose it in a box. Okay. So, by open circuiting the output port, we are able to determine two quantities A and C. Okay. Now, we are left with two more. What are they? B and D. So, what do we have to do? To determine B and D, we will look at equation 1 and 2. We will look at equation 1 and 2. It is very simple. Okay. You have to find out B and D. So, obviously, you have to make V2 0. This has to be removed. What is V2 0 would mean? V2 0 would mean short circuiting the secondary port or output port or a port 2. Alright. So, we will make use of the same equations. We will try to short circuit the secondary port in step 2, and then let us see how we compute the other two transmission parameters, that is B and D. Okay. I will do now what I said. I'll take this equation. I'll copy them. I'll paste here because I keep referring to these equations. Okay. So, we will write the step 2 part. What is my step 2? In the same network, what we do is we will short circuiting port 2. All right. That means what is implied is V2 is made 0. Okay, how do I write it now? I'll have to take the network. I'll take this network. I'll copy the network. Okay. And paste the network. Make it like this, a little smaller. Now what do? I will remove this. Okay. Now I will short the network. Short the secondary port. I'll take a color for this. What I mean is, I'll take a line, draw it here, connect it to this. What has resulted? This has resulted in V2 equal to 0. Okay, so V2 is 0. Now, what we mean to say is, across this port, I'll even remove this. This also I'll remove. Okay? All right. So what we have done here is we have short circuited the secondary port. That is, we have placed a short between 2 and 2 dash. When a short circuit is placed across any element having a certain impedance, it is as good as this being made open, or the role of this is not there as far as the circuit dynamics are concerned. What I mean to say is, whatever current that comes through this from the supply will find an easy path, least resistance path across short circuit and go away. No current would flow through 1 by S. So when there is no current, it is as good as this branch not being there. I suppose that is appreciated. This I'll again copy, paste it here. What I mean is, this can be removed. This 1 by S can be removed. These two are same. This network is same as this network. We were able to remove that 1 by S impedance across 2 and 2 dash for the simple reason that we have placed a short. So when there is a short circuit path available for the current to flow, no current would take any resistive path or an impedance path. Alright, now I1 is there, a current that is getting injected into the port. Now how is the current flow? So current would split because it can see two parallel branches. One branch having an impedance of 1 by S, another branch is this current. So 1 and 1 by S, they are in parallel. Alright, now we will first try to recollect these equations and write what is B and D before we actually proceeding with the equations. Okay, so when we short circuit port 2, that is when V2 is made 0, what is my B equal to? If we can look at these two equations from equation 1, I can clearly write, I'll write it here. Before that, I will shift this network little, I'll make some space. Okay, so what I mean is, when V2 is made 0, with V2 being 0, right, with V2 equal to 0, I can easily write from equation 1 minus B equal to V1 by I2. This I am able to obtain with V2 equal to 0. This is from equation 1. From the other equation, I can write what is minus D. What is minus D equal to? Minus D equal to I1 by I2. Again, this is obtained with the condition V2 equal to 0. So I wanted to, remind you of these two equations because we are interested in getting B and D. So what are we supposed to find? We are supposed to find out the ratio of V1 to I2 and the ratio of I1 to I2. So that is our objective. Okay. So we know what we need to do. Right now we will come back to the network. So this is the network we have. Now how is the current flow? If you look at this network, there is this current I1. It's going to split between two branches. Some current would flow through 1 by S. Some current would flow through 1 by S. And there is going to be some current through this 1 ohm. that it's obvious that when the source is present on one end, the current flow is in this direction. But our conventional current I2 should be into the port. So if we can call the current as I2, I will use a color because it's little, just to be properly understood. I'll write the magnitude of current as I2. But how do I put that direction? Actual direction of flow of current is like this, right? But as the conventional current is into the port, actual current has to be now represented with minus I2 because it is opposite to the conventional flow of current. Alright, if the current was towards the port, then we would have written I2. Now the actual current is flowing away from the port. Away from the port is, it is from 2 to 2 dash. So instead of writing it as simply I2, we will write it as minus I2. So job is done. So now we will try to write the equations. How do we write the equations? How are the things related? So we will try to write the currents, right? So I1 current from the network, I1 current is the sum of the two currents. One current is minus I2 and the other current is the current through this capacitor of 1 by S. What is the magnitude of that current? That current is simply the voltage V1 divided by the impedance. Alright, so this is equal to minus I2 plus S times V1. Okay? Alright, so we need to now see how do we get rid of this V1. Okay, we need an equation for I1 and I2, right? So we need a relationship between an I1 to I2 to determine D. We have I1 here, we have I2 here, but we have this S times V1. Okay, so we need to find out what is this S times V1. Or in other words, we need to eliminate this V1. What is V1 equal to? From this network, if you see, V1 is the voltage across 1 by S. It is also the voltage across this 1 ohm resistance because they are in parallel. I suppose one can clearly see 1 by S and 1. They are in parallel because current is getting divided at one end of these two elements and the same current is getting recombined at the other end of these two elements. By these two elements, what I mean is 1 ohm and 1 by S. So 1 by S and 1 ohm, they are in parallel, I suppose is very clear. Okay, there should not be any confusion. If at all you have such confusion, you please refer to series parallel videos. I have made videos on series parallel networks. Try to see that. Okay, so what I mean to say now is, what is my V1? I can write my V1 as the potential difference across 1 ohm resistance. That is 1 ohm times the current, that is minus I2. So V1 is equal to minus I2. Okay, so we have an equation. We can determine B right now. Right now we can determine. If you look at this, V1 and I2, if you look at this, V1 and I2, if you look at this, so V1 to I2 is talking about minus B. Okay, so we'll try to do further here. So what I mean is V1 to I2 is minus 1. I've taken I2 to the denominator, and if you can look at these equations, V1 to I2 is minus B. So this is equal to minus B. So minus B equal to minus 1, or in other words B equal to 1. So we are able to determine B also. Okay. Now we will come back to this equation. Which equation? We will come back to the equation I1 equal to minus I2 times SV1. Now we will substitute for V1. So what I mean is I1 equal to minus I2 is retained as it is. For S times V1 S, for V1 I'll put minus I2. From here I'll put. So now I'm able to get what I wanted. Okay, this is minus I2 minus SI2. In other words, I will write it as minus I2 times S plus 1. This is I1. And my D is Now the minus d is I1 to I2. Okay, so minus d is nothing but I1 to I2 from the above equation can be written as minus into s plus 1. I have simply taken I2 to the denominator. I1 to I2 is minus s plus 1. Minus d equal to minus s plus 1. So what is d? Simply s plus 1. Therefore, d equal to simply s plus 1. And that completes the problem. Alright. So we'll put the things together. Okay. So what do we have? We have a equal to, the result is a equal to, eventually it is a equal to, what is a? Where is my a? A is s plus 1. Oh, you see a and d are same, huh? A and d equal to s plus 1. We can club the two things together. What is b equal to? B equal to 1. What is c equal to? S into s plus 1. And that completes the problem. Okay, so we have determined the transmission parameters are ABCD parameters for the given network. It's such a simple thing. That's why students find two-port networks very, very easy, because there's nothing in two-port network except that there are relationships which you need to remember, basic relationships between the parameters and the two-port parameters and the port quantities that you have to remember. And all you have to do is apply KCL and KVL and eliminate the variables which are not needed and obtain the ratios. So that completes the problem. Hope you have understood this problem. I'll try to, be regular. Okay, I'll try to be regular and make more videos. Okay, there were comments from my students asking me to upload videos, and for some reason I couldn't do it. Now I'll try to be regular. Okay, all right, thanks for watching. If you have any specific problem, you can simply post them. I will be too happy to take up these problems. All right, see you in my next video.